And now we will also derive that if you had done the same using the training observations, right. So the case 2 was when you are going to estimate the. So now we are looking at what happens if we look at the training observations, right. So again we are interested in this quantity, we cannot estimate it because of this. So we have approximated using these 3 terms, and now the first term. So now we look at the case when we try to estimate that expectation from the training data, right. So what do I mean by that? Again, making things clear, we are interested in this quantity, I cannot estimate it because of this f of x here. So I have expressed it as a sum of these 3 quantities, and now the first quantity, which was an expectation, I am going to empirically estimate it using the training data. So using the n training points, okay, that is what I have put here, right. So this is the empirical estimation of the error from the training data. This is again a small constant, and now we have this quantity here. Now earlier we showed that this quantity becomes 0 because we showed that these two are actually independent. And why were those two independent? Because epsilon was y minus f of x, right, and the other quantity was f hat of x minus f of x, and we argued that these y's, which are actually coming from the test data, did not participate in the estimation of f hat x. Hence these two quantities were independent of each other, right. But now we cannot make that argument, because y, which is coming from the training data now, has actually participated in the estimation of f hat x. So now these two quantities are not independent, hence epsilon and this quantity is not independent, hence I cannot write this as a product of the expected value of epsilon multiplied by the expected value of this quantity, and then this will not become 0, hence the whole term will not become 0, right. So now when you are trying to estimate it from the training data, this term is not disappearing, right. So now y minus f of x is not independent of f hat x minus f of x, because the training data was used for estimating the parameters. So now these two quantities, this expectation cannot be written as this product, and hence it will not be 0, and hence the empirical train error. So now what is that empirical train? If I had assumed, if I had just done this approximation, right. So if you had asked me, hey, what is the error of your model, and I had said, oh hey, this is the error, I have computed it from the training error, I have estimated it empirically from the training data, then actually you would have been way off. Why? Because this quantity is not 0. So if this quantity is high, then your estimate would actually have been way off. Your error would have been the empirical error computed from the training data plus this quantity, but what you have reported is only the empirical error computed from the training data. You did not report this quantity, you do not even know how to compute this quantity, right. But there is this quantity sitting here which you cannot ignore now. In the case of test data, you are able to ignore that. Hence if you had reported this as the test data, then your true error, your whatever estimate you got would have been very close to the true error as we showed on the previous slide. But if you are going to estimate this from the training data, then that is not the case, right. So that is what we have learned, and we had this intuition that training error as computed from the training data, this is the empirical training error, is actually very over optimistic, because it does not consider this other quantity sitting here, right. And test error is not optimistic, because in that case this quantity disappears. So whatever you get from the test error is actually very close to the true error that you might get from the expectation. But now how is this related to model complexity, right. So I said that there is, when you are trying to estimate it from the training error, this quantity sits here, but then I also said that as your training model complexity increases, your training error is overly optimistic. What does that mean? That as your model complexity increases, this quantity is actually very high, and hence if you look only at the empirical estimation from the training error, then you are being very optimistic because you are ignoring a large quantity. But now why does this quantity depend on the model complexity, right? That is something that we have not seen. So that is what we will see next, okay. So now we will try to wrap up the discussion on bias variance by talking about how the true error is actually, what is the relation between the error and the model complexity, right. So this was the quantity that was bothering us, right. This was the quantity which did not go to 0 in the case when we are trying to estimate these expectations from the training data, and then it that meant that if you just compute the empirical training error, then you are missing out on things, right. You are not really giving a true picture of the true error, right. So this was the quantity that was bothering us, And now this quantity again, I could think of it of estimating it empirically, right. So what do I mean by that? I could again think of this as summation I equal to 1 to m or n epsilon I f hat of xi minus f of xi. I can think of estimating this quantity empirically. Okay, this is just a comment, right, just an observation. Now, why this I am making this point is that there is this lemma called Stein's lemma. We can show that yeah, this should have been, sorry, n, because we had n training samples, and this should have been average. So what we can show that this quantity, which is the empirical estimate of the expectation, is actually equal to this quantity. Okay. Now this is a joke that I have every year with my students. You don't ask me what Stein's lemma is, and I will not ask you what Stein's lemma is, but we just, for this discussion, we just need to take it for granted that Stein's lemma says that this expectation that you are interested in is actually equal to this quantity, right. Now if you take this on face value, if you just assume that Stein's lemma is good, is correct, then from here on let's see what answers do we get, right, where do we reach if we assume that this is actually correct, and this is actually correct because Stein's lemma has proven this, right. Okay. So now if this is indeed correct, then what is happening here, right. So when will this quantity that you have here, this quantity, right, which is the same as this quantity that you have, when will that be high, right. This is a derivative. So what does that mean? That if you have a small change in the observation, right, if there is a small change in the observation, then it causes a large change in the estimation, right. So if your yi, right, so you are given this xi comma yi pairs, right, and now if there was a small, suppose you are given the xi as 10 and the yi was 20, right, and instead of that, now if the xi was 10 and the yi was 20.1, this is a small change, right. What this says is that if there is a small change in yi, there is a large change in the estimated value, right. So you are now, your training data has changed, instead of this you had this point, and now ideally you would expect that whatever f hat x you got, right, that means whatever parameters you estimated, that shouldn't change much because there is a very small change in the data, right. But when would this quantity be high? If this quantity is high, it means that if you have even a small change in yi, you are seeing a very large change in your f hat, which means you are seeing a very large change in the w's that you have estimated, right. And this is not good, right. This is definitely not good, because for this much small change, you don't want the model to vary a lot, right. And for what kind of models we saw that this happens, that a small change in the data could lead to a large change in the f hat x that you got. This is what we saw in the case of when we were discussing the first example of simple and complex models. So when we had the simple model of y is equal to w1 x plus w naught, and then when we trained it, we had a total of 500 training samples, and then when we trained it using 30 different samples, this line did not change much, right. That means my f hat x did not change much, right. But the same experiment, then when we repeated it with a complex model, right, which was x raised to 25 all the way up to w naught, we saw that when we take these 30 different samples, which is the same as saying that I am changing the training data, right, and when I change the training data, my estimation was changing a lot in the case of the complex models, right. So hence this quantity you can say is going to be high for complex models as compared to simple models, right. So that's what we are concluding from these 2 points, right, that the expected quantity that we were interested in, which does not go to 0 in the case of training data, is actually equal to this quantity. And now we see that this quantity has this sensitivity term which says that if the small change in yi, what happens to the change in f hat, and we are making this observation that this quantity would be high for complex models because a small change in yi was causing a lot of changes in the estimated value of f hat x or the estimated values of the parameters, whereas for simple models it was not causing a lot of change, right. So connecting these observations, now we can say that this quantity that you see here is actually going to be high for complex models as compared to simple models, right. In complex model would be more changes. So just to So what does that eventually mean, right? So on the previous slide we had that true error is equal to empirical train error plus a small constant plus some term, and now we are seeing that this term is actually proportional to model complexity, or it's a function of model complexity. So I'm just going to write it as omega model complexity, right? So just to indicate that this is actually dependent on the model complexity. So higher the model complexity, larger this term would be. That means your true error would be farther away from the empirical train error. So you would estimate the train error and tell me, hey, it's almost 0, but I will not believe you because you have not told me anything about this quantity. You have only estimated the train error, which is given by summation I equal to 1 to n yi minus y hat I the whole square on the training data, right? You have not given me anything about this. So even if you tell me that, hey, your training error is 0, I will not believe you because this quantity has not been accounted for, and I know that higher the model complexity, this value would be high. That means more complex your model, more farther away would your empirical estimate of the training error be from the true error, right? And just to make sure that this indeed happens, that complex models are actually more sensitive to changes in the training data as opposed to simple models, let's just take a look at that, right? Let's just try to see that. Yeah. So now what I have taken, this is some training data that was given to me, and I estimated the true model, I estimated the complex model, which is the red colored model, and the simple model, which was the green colored model. Now what I have done is, I have changed one of these data points, only one of the data points, right? I have, instead of taking x comma y, I have taken this x comma y, right? And now you can see that my simple model has not changed much, right? So my f hat of x, so I changed y, but my f hat of x did not change much. That means this quantity is going to be small, right? But for the complex model, my estimation has changed quite a bit, right? So now when I changed y by a small quantity, my f hat x has also changed dramatically, right? In this region it's very different from what it was originally, right? So hence for complex models, small changes in the training data could cause a large change in the estimated function, right? The f hat x or the estimated values of the parameters, right? So that's just a empirical demonstration or an anecdotal demonstration of this idea that complex models are more sensitive to changes in the training data, and that's the quantity that bothers us. So this quantity, maybe I should go to the next slide. I'll go to the next slide. Okay, I can just do this slide first, right? Okay, so hence while training, instead of minimizing the train error, we should minimize this error, right? So now if you're going to just focus on minimizing the train error, okay, you might make it 0. Okay, so now what is the what is your true error, was the expected value on the right hand side, is actually equal to the train error. So this is what my train error is, right? My train error is I equal to 1 to n, sorry, I keep changing m and m, but I sure you understand what I mean. This is what L train is, and what I was trying to do is I was just trying to minimize this. But now I have realized that if I try to minimize this and make it to 0, there is this another quantity which is dependent on the model complexity, which keeps increasing. So in effect, my expected error is increasing, right? So I might have done a great job of reducing this to 0, but at the cost of increasing this significantly, and then the net effect is my model is still bad. When I am going to pass it test instances which were not seen during training, this expectation is going to be, this error is going to be still very high, right? So that's why you should not try to just minimize the train error, but train error plus the model complexity is what you should try to minimize. Now how do you encode this model complexity? I just define a generic function which says that this captures the model complexity. Now how do you define model complexity is something that we will see as we go along, but the main idea here is that you should not just try to minimize this error, but you should also try to minimize the model complexity. And yeah, this omega theta would be high for complex models and small for simple models. So if you have complex models, this quantity would be high, and hence your the loss that you are trying to minimize is still going to be high. So it will not allow you to make the models very complex, right? And this acts as an approximation for the quantity that we just saw, right. So this is the model complexity term that we had seen, and now you have to come up with some functions which act as an approximation of this, and when you are trying to reduce this, it actually decreases the model complexity, which means it will decrease this quantity, which means it will decrease this sum, right. So you should come up with omegas which decrease the model complexity, because if the model complexity decreases, this term will decrease, and hence this term will also decrease, right. So that is the way you are going to handle this complex term here, because directly handling it looks difficult, but you could define some omega thetas such that you are sure that if you minimize that omega theta, your model complexity is going to be reduced, and hence you will be sure that this term that was bothering you is going to be reduced, right. So this actually is the basis for all regularization methods, right. So this is what you do in regularization. Instead of just minimizing L train theta, which is the empirical training error, you actually add some regularization term to that, and then you say that I am going to minimize the empirical train error as well as the regularization error, because that will make sure that my expected error, which is what I was interested in, is actually going to be small, right. And the pictorial view of this is the same. So this is what would happen if I were to just look at the training error, right. So this is L train, which is computed just using those n training samples. Then as I keep increasing the model complexity, this will keep decreasing. But what will happen is, as I increase the model complexity, this quantity is going to increase, and hence my error is actually going to be high, right. So I need to find this sweet spot, and this omega theta should ensure that this model complexity is reasonable, so that you have low training error, but at the same time this quantity is also not high, and hence your expected error is also not high, right. That is why we use regularization. Now why do we care about regularization in the context of deep learning, right. Why am I teaching you this in the context of deep learning? So the answer to that is simple, right. So deep learning, we said that regularization is basically trying to control for model complexity, and in deep neural networks you know that these are highly complex models. Why are they highly complex? Because they have many layers, many nonlinearities, and many parameters. So they can completely overfit, right, because this we also know from the universal approximation theorem, that you can completely overfit your training data, right. You can get arbitrarily close to your true function if you keep adding layers or if you keep adding neurons, right. And you do not want to do that, right. You do not want to become very close to your training data, because then your test error would be high, and that is why you do not want to overfit, because if you design a very deep neural network with many neurons, many parameters, then it will be able to drive the training error to 0. But while doing so, you have increased the model complexity by adding many parameters and many layers, and that is going to give you poor generalization capability, or poor or a higher test error. That is why you add regularization, so that you control for model complexity. Now what are these different regularization methods that you can use in the context of deep learning is something that we will see in the next lecture. Thank you. So I will end it here, and I will see you in the next lecture.